Hey guys, what's the crack? So in this video, we're going to go over some of the required practicals, okay? Just like different parts of knowledge that you need to know for them. And they kind of apply, the same type of stuff comes up in the other practicals, even not going over it. Okay, so first one, this is our double slit experiment. Or it could be the single slit, or it could be the diffraction gradient experiment. They can basically ask you either one of those, and it's the same principles, right? Because what we have here is our laser light, our monochromatic light, light of a single wavelength. Let's say it's red because my pen is red. It's going to hit a double slit, or a single slit, or a diffraction gradient. And what's going to happen, we're going to get waves that superpose. And what we're going to happen then is on our screen, we're going to get our central maximum and then our alternating bright and dark fringes. Okay, so one question they might ask you is, how do we ensure that our screen is perpendicular to the floor? Okay, anytime you see the word perpendicular or right angles, you're thinking of set squares. So you might have seen a set square before in one of those little math packs. So those little math packs, they got like the wee ruler in it, a rubber, a sharpener, sometimes they got the protractor in it and a compass. You've probably seen a little set square in there. You probably didn't want to use it for before because you barely use it in GCSEs. You might use it as a ruler because it does have a little ruler on it, but it basically is used to make sure that you have a perfect right angle. However, you can get them in really big sizes. They're not just tiny, okay? You get them really large sizes. So what I want to use is I want to use my set square, and I can place my set square here to make sure that my screen is perpendicular to the floor. So again, what that's called is a set square. Okay? Set squares, they really like in AQA, especially AQA. It comes up like basically every year. So in AQA, if you're doing paper 3, section A, and you've not mentioned a set square anywhere in your exam, just flip through it again to make sure nowhere did it ask you to make sure that things are perpendicular or if things are sitting at right angles. If you're doing Edexcel or OCRA, it can come up anywhere in the papers. Okay? Another way they might ask you about making sure that this is set up properly is instead of asking you to make sure the screen is perpendicular to the floor, something they might ask you is to make sure that the beam is parallel to the floor. Okay, so my beam of light is parallel to the floor. Okay, so basically you're trying to make sure that your laser is not tilted at an angle. So you should be looking at this thinking, how can I make sure that beam of light is parallel to the floor? Okay, because we can't measure the height of light, but you should be able to think, I can measure the height of those dots on my screen. I can measure the height of the laser from the ground, and if both of those heights are equal, that's how we know that our laser light is parallel to the floor. Other things I might ask you is, how can we measure or how can we improve a way to measure W? So remember what W is, it's the separation between those fringes. If you're doing OCRA, it doesn't use this equation. OCRA uses X equals YD over A. So if you're doing OCRA, it'll be asking you, how can you improve how to measure X? Okay, so in OCRA, just imagine that X right now is my W. So in AQA, they might say, how can we improve a way to measure W? And a way to improve measuring W is clearly, we want to reduce the percentage uncertainty in our results. So what is percentage uncertainty? Percentage uncertainty is the absolute uncertainty divided by your value multiplied by 100. Okay, you always want your percentage uncertainty in your results to be as low as possible, right? That tells you your value is more accurate. The only way to get this as low as possible is to make sure your value is as big as possible. So example, when I'm doing my pendulum experiment, I'm not going to just measure the time for one swing, I'm going to measure the time for multiple swings, maybe 10 swings to get a really high value. For here, I'm not going to measure the width of one fringe, I'm going to measure the width of several fringes. So maybe I measure the 1, 2, 3, 4. I measure 4 fringes, and then we just divide by 4 to get the width of a single fringe. Another thing we could do is we could try to make this distance much bigger. So what I want to do maybe is just spread out my pattern. So maybe I just want to make that W a much bigger value. So I look here and think, how can I make W a bigger value? So again, my value is bigger, so my percentage uncertainty is lower. To make W bigger, either we can increase the wavelength of light, okay, so increase wavelength of light, but if I actually had this experiment, there's not a wavelength of light that's longer than red. So I already have the longest wavelength of light. Another thing I could do, like I could increase D. So D is the separation between our slits and our screen. So one thing I could do is I can move that distance between my screen and my slits much bigger. So then my W's are much further apart. My fringe spacing is much further apart. So I get a bigger value. So multiple ways there that we could get an improved experiment. Okay. So again, percentage uncertainty, they really like on these practicals. So just make sure in your papers, if you've not mentioned percentage uncertainty anywhere, you look through your paper to see, is there any way that I can take bigger readings or more readings to reduce the percentage uncertainty? Okay, they really like that sentence. So again, we mentioned here, let's say we're doing our pendulum practical. So T is our time period. So time period. Remember, time period is the time it takes for one full oscillation or one full circle or one full wave. 2 pi L is our length of our string, and G is our acceleration due to gravity. So let's say we're doing this experiment, trying to find out what acceleration of gravity is. I'm going to change the length of my spring and record the time it takes for one full oscillation. Again, one full oscillation, if it starts here, is when it goes through its equilibrium, goes the whole way to its maximum other side, and then goes the whole way back again. So that's one full swing, okay? But again, I shouldn't just record the time for one full swing because I want my percentage uncertainty to be as low as possible. So I make sure I should time multiple swings. So maybe we're going to time 10 swings or 10 oscillations. And then to get the time for one swing, we just take our value and divide by 10. But we know our percentage uncertainty is going to be really low because our value was really big. And the absolute uncertainty, remember, is the absolute uncertainty in your equipment. So let's say I was using a stopwatch, and my stopwatch for my 10 swings says 5.02 seconds. So what I would do here to find the percentage uncertainty is I do my absolute uncertainty, which is the uncertainty or the resolution of my equipment, which here would be 0.01, divided by the value, 5.02, and multiplied by 100. So you can see, if I did 10 swings and got 5.02 seconds, that makes this value really high. So what it does is it makes my percentage uncertainty really low. But that's the time for 10 swings. So if I took the time for one swing is that value divided by 10. So that one swing divided by 10 is going to be 0.502 seconds. But you can see, if I just did my, well, that can't really be the reading because of the uncertainty in the equipment, so 0.50. But you can see, if I put 0.01 divided by 0.50, that percentage share is much higher. So again, that's why we take multiple swings to make that percentage uncertainty as low as possible. Other things. They might say that when you let go of this pendulum and you let it start swinging, so again, you've got to imagine a pendulum swinging, why should you not record the first oscillation? And you shouldn't really record the first oscillation in case it's swinging in a loop, okay? Or maybe it takes some time to that string to fully get taut, okay? So you shouldn't record the first oscillation because it might not be oscillating in the one plane. So you normally just want to ignore the first oscillation and then count your timing. Okay, things to help us count the time is we need to use a thing called a fluidal marker or fiducial marker, however you want to pronounce it. Okay, so you're thinking, should I start recording the time it gets from, starts here, goes the whole way to the end and back again, and that's going to be my little fluid marker and I count there? Or should I do it from the center of motion every time it passes through the center? And hopefully you're thinking it's actually going faster here, okay? So it's going faster here because remember, when things change direction, they slow down. For example, if I throw a ball up, my ball goes up. When it gets its maximum height, its speed is 0, and then it comes back down again. So again, when it's changing direction, its speed is 0. So when you're recording your oscillations, you actually want to record it through the middle. So that's when you're going to put your fiducial marker. You want to record it through the middle because that's when it's going faster. So again, what would happen is it starts here. Well, I'm going to start my pendulum off, goes through here. I'm going to start my timer through here, back, 1. Here, back, 2. Here, back, 3. Here, back, 4. Okay. Other things I might mention is why should we make sure this angle is really small? Okay, so again, you want to make sure the angle is really small because if you pull that pendulum to really high heights and let it start swinging, clearly you're going to have air resistance taking a big value in there, a big chunk of your data. So again, you want to make sure that you do small angle oscillations. Because again, I want to make sure that I ignore air resistance, okay? Or have air resistance at minimal, basically. Okay, speaking of air resistance, another practical you might see is that practical where you basically drop an object in free fall and you want to figure out what that acceleration is to gravity. So let's say we have a ball bearing here, so it's just like a little tiny ball. It's being held up by an electromagnet. So we know an electromagnet basically just is you have wire, you have current flowing through it, and we create a magnetic field. So what might happen is we might turn off our electromagnet. When we turn off our electromagnet, our ball is going to get dropped. And it's going to drop through a height and hit a tracker pad in the bottom. When it hits the tracker pad in the bottom, it's going to be connected to a timer that's going to then stop the timer. Okay, so again, my electromagnet is going to be connected to my timer. And as soon as I turn off the electromagnet, it's going to start my timer. as soon as it hits the tracker pad, it's going to stop the timer. So I get the time it takes for that ball to fall through that distance. Problems here is that you know when you demagnetize electromagnet, when we turn off an electromagnet, it doesn't just demagnetize straight away, it stays magnetic for a little time. So one thing is the time that it takes this ball to drop is going to be too high. So my time value is going to be too high because it's going to take some time for that electromagnet to demagnetize, right? It doesn't just drop the ball instantly. Another thing is when we're measuring the height the ball drops through, what I want to do is I don't measure from the electromagnet to the tracker pad. That's wrong. What you want to do is you want to measure from the midpoint of the ball bearing to the bottom. Okay, so again, the best way to do this is take a ruler, measure from the bottom of the ball bearing down to your tracker pad. So I'm going to record that height. But again, I said from the midpoint of the ball bearing. So I need to include somehow what that radius of that ball is. And the best way to find the radius of the ball is what I should do is I should take my micrometer, and I'm going to find out what the radius is. Pardon me, I'm going to find out what the diameter is of that ball with my micrometer. And then all I do is take my diameter and divide by 2 to find out what the radius is of that ball is. And then I'm just going to add the radius to the height to find out what that S is, what the distance it fell through. So again, my S, the distance it fell through, is going to be my R, my radius of my ball bearing, plus my height. And I found that using my ruler and my micrometer. I made an earlier video on micrometers if you want to go back there to look at them. Okay, hope you're thinking the ball drops from rest, so U becomes 0. So what we have now is that our R plus H, the distance it falls through, is going to equal 1/2 of A times T squared. Again, we have our time because our time is going to be our tracker pad. So if we did this experiment, one thing I could do is I could plot my R plus H, which is the height that it falls through, against the time squared, and I can see my gradient here is going to be 1/2 of A. So again, that is my gradient. So if I want to find what that acceleration due to gravity is, I just have to do 2 times the gradient. Problems with this is the height, okay? So again, if we think about this height that the ball falls through, that R plus H, okay? So the height that the ball falls through here. One thing is you want to make sure that the height is not really big, right? So I'm never going to drop it from the top of a building, because if I drop it from the top of a building, I know that air resistance is going to take part. And I know eventually what's going to happen is that ball bearing is going to reach its terminal velocity. And terminal velocity means it's no longer accelerating. So if my ball bearing is no longer accelerating, I can't get a value for G, the acceleration due to gravity. So I need to make sure the height one is small enough that it doesn't reach terminal velocity, but I can't make sure the height is too small because then I'm going to get a really high percentage uncertainty. So I need a value that's high enough that it drops through to give me a low percentage uncertainty, but not too high of a value because then it's going to reach terminal velocity. Last one. Last one is if we're looking at our EMF. So let's say we want to find out what the EMF is of our cell. So again, we know cells aren't perfect or batteries aren't perfect. They have some small internal resistance. So let's say I want to find out what that internal resistance is, or I want to find out what the EMF is. One thing we do first, if the current becomes 0, so if the switch is open, the potential difference across the cell is going to equal the EMF. So if I just keep my switch open, whatever this voltmeter reads is going to be the EMF, right? So it's one nice way to do it. Or what we can do is that we can take we can close our switch, take values of current and our potential difference across it, and get loads of value for current and our potential difference, and we can figure out what EMF and our resistance is. So let's say we do it that way. So again, if I want to plot loads of values of current, loads of values for potential difference, what I can do now is I can plot a graph of my results. I know y is equal to mx plus c. But I don't like this form. I need to make it look like this form. So I'm just going to rearrange that now to say v equals EMF. No, I want to move it to look like that equation. So V equals negative IR plus the EMF. So now I can see I can line these up quite nicely. So what I can see is I plot a graph. If I plot a graph on my y-axis of my potential difference, so on, let's put it here, my y-axis of my potential difference, and my x-axis, I'm going to put my current. So my x-axis, I'm going to put my current. I can see that my y-intercept is going to be the EMF, and my gradient is negative R. So my y-intercept is going to be the EMF, and my gradient is going to be negative R. So if I want to find what the EMF is, I can just find out what that y-intercept is. and I want to find what r is, I just have to take negative values of the gradient. Remember, to find the gradient in these practicals, you can't take a little triangle. Again, because if you take a little triangle, the percentage uncertainty is going to be really high because that value is really low. So what you want to do is you always want to take the biggest triangles possible. And they do look at this in your test. You want to make sure it's bigger than at least 5 centimeters on one side. Okay, so take the biggest triangle possible to find the gradient. You're changing your y over your change in x. And just make sure when you're plotting your data, they've actually written this in mark schemes, that you want to make sure your pencil is sharp, not blunt. So just make sure when you take your pencil into your exam, you have a sharpener with you as well. Okay? So, hope you find it helpful.